Okay, there we go. Thank you for reminding me. I would have forgotten. So I will be recording this, and I actually have some, I think they might still be on the 420 syllabus, unsure, but I have some other Altium tutorial videos on YouTube, which once I get this one uploaded, I will send out the link to that one as well. They are painfully boring, dreadfully so. But I've gotten a lot of feedback that they have been useful to teams in the past. So in addition to this, you will have access to those, and hopefully that will be a good combination of resources for you. Okay, we are at 7:34. I'd say we'll get started at 7:35. Just for anyone coming in, I want to reiterate that please feel free to ask questions as we go through. Most questions aren't dumb questions. So please feel free to ask questions.
Hey, Matt, this is Garth Crosby. How are you doing?
Hey, Dr. Crosby, how are you?
Pretty good. I just came by to say thank you for doing this. And I won't be able to stay the entire duration of your session, but I really appreciate this. So thank you, and I hope it all goes very well.
Yeah, no problem. This is all good fun. Okay, so it is now 7:35, so I elect that we get started. I see we have 26 people. That's a good number. So real quick about me, I graduated ESET in 2019. December 2019. I now work at Raytheon as an electrical engineer, and I work specifically in test equipment and sustainment of systems that get broken in the field. And then I also continue working projects with Professor Leonard's T-Star. So that's a real brief about me. No one cares about that. Moving on. So the board we're going to work on is, I'm calling it the USB MUX, as the little logo here indicates. Basically, I have, as all capstone projects are, I have a problem. And my problem is I work from home mostly, and I have a great setup of monitors, of computer monitors. And so I like to use my computer monitors with both my work laptop and my personal desktop. Which is great because they have multiple inputs. That's all good. But that means I'd also like to be able to use the same keyboard and mouse. Now, I already have the keyboard and mouse plugged into a USB hub off to the side, but right now I have to do the excruciating task of moving it from one computer to the other when I want to switch between the two. So what this board will accomplish is, with these little switches here, I will be able to select which computer my peripherals, my USB, and in fact, the mic I'm talking through, and my keyboard and mouse, which computer they will be directed to. And so simple requirements: it needs to be able to accept a USB-A, so the big fat connector you're used to for USB. That's the connector that's on my USB hub. And it must be able to switch that USB hub between at least two computers. It also should be reasonably small. That's pretty open-ended. With some of your customers, you may get a more specific requirement than reasonably small. But for my application, I just wanted it to be as small as it realistically and reasonably can be. And I've made some awful diagrams here. So we have, this is our conceptual block diagram. So you can see my keyboard and mouse are plugged into a USB hub here. And I want this to then, instead of connecting directly to a computer, I want it to plug into this USB switch. And then that switch should connect to each of the two computers I have. And on that switch, I should be able to, as the name implies, switch between them, right? Okay. So, then we have to, we'll get to the functional block in a second. Then what we have to do is make a few decisions. One of which is, I could probably, actually definitely, I could do this all analog, but where's the fun in that? So I want to find a device, a surface mount integrated circuit that will switch between the two computers for me. And presumably in 219, we all learned about multiplexers. So that's really what I'm looking for, is a multiplexer. In fact, I want a dual channel multiplexer because USB has both a data positive and a data negative, right? So if I recall, I literally Googled USB multiplexer, and what I came, and there, you'll have 100 different options just poking through for this specific requirement. Obviously, I'm looking for a USB, and I picked USB multiplexer because I know it's it passed all tests to prove that it works well with USB. I could use a normal dual channel multiplexer. That would probably work fine, but this way I know it's certified to work with USB. So what I've found here is the Maxim or Max 4899. It's a pretty cool little chip. The way, and again, it's just a multiplexer. There's nothing too exciting about it. I don't know if they have a good diagram in here, but as it says on the top, and I'm sure most of you hate data sheets. I recommend you learn to at least tolerate them, because they're extremely important to be able to read. And one of the most, when you're looking at a data sheet for an IC, especially a relatively simple IC like this, a few things we want to look at. I want to look at my operating current. This one has a ridiculously low operating current, so that's good because almost any voltage regulator I pick will probably suffice for this. Now, it is a TQFN package, which, hang on. Let me go here. TQFN package. This is something else you can pay attention to, is what that looks like. Now, some of you will be skilled enough to solder that. Some of you will probably have your boards professionally soldered, but some of you are not skilled enough to solder that. That's okay. And so that's one thing that you need to consider when you're selecting your parts. Actually, here's a great little image. Well, that did not make it any bigger, but like you've seen dip before, those are through hole. We're talking about a QFN right now. These SOT 23s, if you want to write that down, SOT 23 or an SOP, I guarantee you can solder those. They're pretty easy. So all that to say, that's one thing you need to factor in when you're selecting your parts. And some parts do come in multiple different footprints. In this case, the Max 4899 only comes in a QFN. And we can see all that data down here at the bottom. There'll always be a package information bit. And so this particular device only has one package offering, which we can see there. So I have selected this part for this application, and I think it suits the application well. It meets all of our requirements. It is intended for USB. 2.0 is sufficient for me. I don't need 3.0. If I want that, I'll plug directly into the computer. And has nice low current draw, which I don't really care about, but it's kind of nice to have. And yeah, so, okay. So we've selected this one. We should retain this data sheet, maybe save it to a folder. And then now let's go back to here and we'll go to here. So I know that I need a number of things, right? So I have my Max 4899. Now, one thing about it is USB is typically 5 volts. My Max 4899 wants 3.3 volts per the data sheet. So I know I need to generate 3.3 volts, which is frankly annoying because it'd be nice if I could just take the 5 volts from USB and just pipe it over. I know it doesn't take hardly any power, so that's no big deal. Can everybody still see? Something just popped up on my screen.
Yeah, we can see.
Okay, good. Thank you. So I know I need to generate 3.3 volts. Great. So fine, whatever. So I'm going to show you a method that I recommend using if you're dealing in relatively high power. And by high power, I mean maybe 2 amp plus. If you need to generate a power supply, or if you need to put a power supply on your board, and this is something else to write down. I highly recommend Googling TI Webbench. There it is spelled out right there at the top. And what's cool about this is, well, let's just take their, no, I'm sidestepping a little bit here. I'm not going to use this in this particular project, but you need to know that this exists. So, so let's take, they're just pre-selected inputs here, and I'm just going to hit view designs, and it'll take a second. And then several designs will pop up. Now, remember what I talked about can I solder the part? So because I'm thinking about that, I'm going to go down here to IC package, and I'm going to, let's see, what do they got that I like? Well, let's say that I'm okay with the QFN. So I'm going to select all the QFN ones, which is, again, what we were just dealing with the Max 4899. And I'm just going to pick the first one. You can go through and look at BOM cost and efficiency and all that. You can compare them. But let's just click on the first one. Oh, I clicked on the wrong thing. Got to click on the actual schematic. And then it'll pull up a schematic for you. It'll pull up a bill of materials. And you can actually go in, you can click customize design, and wait for it to load. Come on now. There we go. And so you can go to bill of materials, and let's say that CN here is out of stock everywhere. So you can select alternate part. You can select this one, say this one's in stock. And you can base your choices on the size. So like 0603 might be the smallest thing a lot of you can solder. But 0402 is absolutely tiny, and 0201 is beyond tiny. So we might select parts that, see the package column over here. Maybe instead of an 0402, I'll come down to either an 06 or an 08, 05 and select one of those, because then I know I can actually solder it. And that, I can't stress enough how important of a factor that is what it's one thing to select, to design your schematic and create your board and all that, but you have to think about the usability and the creatability of that board. And if it's you as an individual soldering it or one of your teammates, then you need to think about, okay, maybe we don't have great microscopes, or we have those digital microscopes that are okay. And I want to make sure we can complete this project well. Well, it's going to be really frustrating when you accidentally picked an 0201 and realize that you should have ordered 20 of them because you've already lost 10, because they are that small. So, and this thing will generate a PCB layout for you. Yeah. So kind of the rule with Webbench is you can select whatever alternate parts you want. That you need, to match your package idealization or whatever. But once you do that, like this part number, you don't get to pick another one. Like, yeah, you can pick it from this list, but I mean, like if you go on Mauser and you find, something with the same spec, but it's not this one, no, don't do that. Because these things are kind of finicky. I've managed to screw them up before myself. And so these are buck regulators. So they have their own. It's not a linear regulator that operates in a pretty straightforward manner. These are much more complex. They run through an inductor, all sorts of crazy stuff. So we need to build these exactly the way Webbench says, and we need to select the exact parts Webbench says. And I accidentally opened that. How do I make you go away? I accidentally opened, was this it? No, this isn't it. How do I go? Well, actually, I do want to show you one thing. Yeah. So, and then on the regulator itself, when you open its data sheet, we're going to go probably all the way to the bottom. And on every one of these regulators, you'll find this. And it's going to say something to the effect of layout example. And we'll get to layout later. But the thing I want you to take away from here is what this says, like, the approximate like relationship physically to where things go. You must do the exact same thing. You must match this layout. I have I have in my past of designing, I have selected the correct parts, but not followed this, and it did not work. Okay. So, so please, please, please just do it correctly from the get-go if you're using one of these designs, and follow exactly what this says. Okay. Okay, so that's WebBench. We're not really dealing with that, but I did want to show that to you because I imagine a lot of you, or at least some of you, will need to know that information. Okie dokie. So I'm going to close all of that. And so again, back to our project, we need a regulator that that will do a 5 volt to 3.3 volt. If you recall, over here we have almost no operating current, so you could pick something. I'll give you all the YouTube stuff probably tomorrow after I upload it, because frankly I don't remember what the channel name is. So we're going to select. I pre-selected this guy. There's a specific one that'll output 3.3 volts. It has what I think it was 100 milliamp. Yeah. It's way more than we need, but it's a nice SO. Remember I mentioned SOT 23, nice and easily solderable. It's just something I selected on Mauser. I was just filtering through. So we're going to go with this one. It looks like it'll work great. And one thing to note about this, and again, you have to be willing to read the data sheet, or at least skim it, is notice that on the application information here, it calls out a 1 microfarad capacitor here on the input and a 4.7 microfarad capacitor on the output. So we need to make sure we do that, and that's for voltage stabilization. We do need to match those values, and the voltage rating of those capacitors should be at or above the voltage they'll be experiencing, preferably above. So, but again, this is just stuff you need to look for when you're going through a data sheet. Okay. Okay. So, what else here? So, I realized I wanted a separate power input because I didn't want to rely on any one device or computer. I'm calling it device in this diagram. I didn't want to rely on any one device's power to power the board, but I also didn't want to combine their powers. So I decided to just have a totally separate, you can see it. It's over here on the side. Has a totally separate power input. That's just because that was easier. And then that goes down and powers the USB-A, which, as you'll recall, goes to the USB hub, which means that external power is just powering my peripherals, but their data goes through the switch. And then lastly, the 3.3 volts goes to the Max 4899. And then we have 2 switches. The Max, there's always a nice Venn diagram. So here it is. And where are they? C1 and C0, they call them, are the digital control inputs. So that means if we apply 3.3 volts, it'll be an active high, or rather just a high. And then when we apply ground, it'll be 0. So we have a 2-bit binary there. So we can have 2 switches, and that will give us our 4 output combinations. Okay, I'm going to pause right there. Any questions so far? How are we doing? That good, huh? Cool. And while we're here, everybody can hear fine, everybody can see fine, all that's good. Cool.
Yep, sounds good, looks good.
All right. So now we're going to the moment you've all been waiting for. We're going to move to Altium. If you haven't done this, and somebody feel free to correct me if I'm wrong, but I'm pretty sure the process was you tell, I guess it's probably Roseanne, who on your team needs to have an Altium license. She'll add you to the directory, and then you'll be good to go. You should be able to install it on your personal computer, or you can use it in the lab. At least that's the way it was when I was there. Maybe it's changed. And then you can log in. You have to make an Altium account, I assume, and then you should be able to go here and then go to licenses and select the licenses that have been given to you. So all that is exciting. So now we're going to just start at the beginning. So we're going to open a new project. I'm going to name this project, I don't know, USB Mux or something. USB Mux. Okay. That's going to do something. Oh, it opened over here. Don't do that. No. Okay. Hang on. Hang on. I have 2 Altium windows open. Okay, that didn't really help me any. Okay, fine. You come over here. Okay. And you come over here. Okay. And you. Sorry. You go here. Okay. So what I did to create this schematic, it opened up this project with nothing under it. You right click on it, you add new to project, and then you click schematic. And I'm going to leave that name sheet 1. Some of you will probably end up with multiple sheets for a single circuit card. That's fine. In this case, we're just going to have 1. But some of you may end up, and that's fine. I've had projects with like 7 schematic sheets and you only end up with 1 PCB document, obviously. And that's fine. So feel free to use as many schematic documents as you need. It's nice to stay organized. So there's no reason to try to cram everything on 1 page. In this case, we have no problem fitting it all on 1 page, but you don't need to do that. Okay, so I think first we're gonna pull in our voltage regulator. Whoops. Oh, it wants us to save the schematic. So sure, sheet 1, whatever. And ideally you'll give that a more intelligent name than sheet 1. Maybe it's your voltage regulator page, whatever. So you click this little place part button at the top. And in the case of the regulator, they have this cool thing. There's a manufacturer part search. So I'm going to click that. And we've already selected the regulator we're going to use. So I'm going to search for that and just type it in 76133DBVR. And what you'll find is it'll pop up a few options. And you'll notice a few things. Firstly, see how it has this little green kind of caterpillar looking thing? That means they have a model. So I can, you always have to do it more than once for some reason, but I can, or maybe not, I can drag that over and boom, there's the part. I didn't really have to do anything. And we can double click on that. And if we go here, we can see that, oh, look at that. It is indeed our part. You can go to 2D mode and see, yep, there's what it looks like. Cool, that's great. But sometimes manufacturer parts doesn't return something useful. So if we go, and that's always at the bottom of the library here, manufacturer part search. So say we look for now the Max 4899. If I recall, yeah, notice that it doesn't have the part. So that means I got to make it. Excuse me. So what we're going to do then is I already have my own library, but what you would do is file new, file new. And then you'll create an integrated library. And that'll give you both a schematic library like you can see here. and we're not going to be able to go through every single detail of everything. Like I'm clicking on things and not explaining them. There's a lot to this software. And the point of this is to kind of, so kind of can get started. I'm not going to be able to tell you everything. That's just not going to happen. But we can see so in the library, you will always have a schematic component and then a PCB component, which makes sense because we need something to go on our schematic and we need something to go on our circuit board. And so you'll pretty much always make the PCB one first. You'll make your footprint. That's what it's called. So like here, we have this just generic 3-pin connector that I made for some reason. And we can see it in 3D mode. If you hit the number, and this is true in the circuit board part too. So right now I'm on this. If I hit the number 3 key, we're in 3D mode. I'm holding the shift key to pull up that. You can move it around. If I hit the number 2, then I'm in kind of the edit mode, the 2D edit mode. So that's the number 2 key and the number 3 key. Okay. That's a useful little shortcut for you to have. But what we're doing here is we don't have the MAX 4899 like it wasn't in the manufacturer part search. You might be able to Google it and find it somewhere, but we're not counting on that. So what we can do is we'll go back to this guy and we'll go down to down to the package information here, and you'll see that it has a bunch of dimensions on it. And so based on which specific part number you're using, you can, determine what D2 is, for instance. This is very straightforward. It's easy to read. It looks kind of complex, but Altium has a cool tool. You go to tools and you do the IPC compliant footprint wizard. And we know we're doing a QFN. There's a bunch of different options. So we know we're doing a QFN. So we might hit next. And then I'm not going to go through it, but I think you can probably see what we're doing here. Like they say body span range. And when they say range, they mean it'll usually give a plus or minus, or in this case, it gives a min and max. So that's your range. For whatever dimension this is, it's 0.25 to 1.25. That's usually millimeters, but try to find the letters MM or IN written somewhere on the page so you can confirm what unit it's in. But in this case, I know for a fact it's in millimeters because I already did this. So you just fill in that information. It has a little diagram over here for you, and there's 2 pages of that. And then you can go through, and then the only other page we really care about is the footprint dimensions page, which I don't remember. Did this one have a dedicated layout? No, it didn't. Sometimes it has package information, and then it also, like, that's what this is. And then it also has a recommended footprint, and it'll give dimensions for that. And that would be the dimensions you put into Altium. If you don't want to, like, if you have it, then put it in. If you don't, just use their calculated values, and that should be fine. So that's how you go about making a part in here. And then you can go on to create a schematic element for the Max. There it is. I created this. There's some buttons at the top. You place a pen, there's a pen. You can renumber it. You can rename it. It's pretty straightforward. And you give it a pretty little box, and you just make sure your pen numbers line up with what's on the data sheet. You can place them wherever you want on this box. As long as they have the right number, you're fine. And then you want to make sure you add a footprint, which is the one we would have just made in finishing that process. So you go to you go to add footprint, and then you pick the one you just made. And the last kind of goofy thing you have to do when you finish making a part is you go up to your library project and you compile it. And once you compile it, it'll it'll compile those two parts together and it will add it to your library, which you can access over here. Whoops, wrong drop down. I messed up. There we go. Again, this button is your place part button. And we can drop down. These two libraries come with Altium. This one's mine. And these are all the parts I've made. So I know, and Altium has, this is actually worth noting, Altium has excellent documentation on their website. So oftentimes if you have a question on how to do something, even if it's a very specific something, usually you can successfully Google that. They have really good documentation, Altium does. So make sure you always give that a shot. So there's our max for it, $48.99. And then what else do we need? We need some switches. So you would, I don't know, maybe look at past capstone projects for switches you like, maybe rummage through your own personal parts bin, look on Mauser, look on Amazon, and find you a switch you like. For this application, because I am a nerd, I happen to have some stock of switches. So, and I happen to have some of these EG 1218s in my drawer over there. So I'm going to use those because I have them. And then what else do we need? We need some connectors, I guess. So another cool thing about the manufacturer part search is I can just type USB-A, hit enter, and a bunch of stuff will pop up and you can kind of pick between them. In fact, that might be the one, 4044, 16021. Yep, this is the one I used. So there's my USB-A. And so, yeah, it was that easy. And then I know I need a USB micro. And I think I picked one further down. So I think I'm going to actually search this one. 6291051.
Hey, can I ask a question real quick?
Sure.
The little green bars, you have the green next to that, what you call a caterpillar.
Yeah.
I saw an orange one and a red one. What does that indicate?
So good question. So if I click on this little down arrow here, I can see okay. Yeah. Thank you for pointing that out because this might be one of the coolest features. This is showing real-time inventory of this part at various different suppliers. So here you can see DigiKey has it, and green means obviously in stock, orange means limited stock, and red means no stock. RS Components, Newark. I don't know why there's more than one for different suppliers. I couldn't tell you that, but we can see that Mauser has it in stock. So yeah, so that's what this is. And it's green because it's determined there's sufficient stock out there for it to be green. So yeah, that's a super cool feature of manufacturer part search.
So you can actually order it directly from the software, or do you need to go to that website directly to?
You have to go to the website directly, and I imagine if I click that, it'll take me. Yeah, there we go. So it'll take you to the part, which is cool. But what I think is especially cool is in Altium you can generate a bill of materials, and because you're pulling this from manufacturer part search, it'll pull all the data. It'll pull current pricing. It'll pull like what suppliers have it, all that stuff. So when you go to order parts, it's easy to pick where you're going to buy it from. So no, I don't think you can order it directly from here, but it has some cool benefits. So good question.
All right, thank you.
Yeah. So let me double check the part number on this. 62910513681. Okay, cool. By the way, you can have Altium it's kind of like a Google Chrome where I can pull this tab and move it to a different screen. So you can have multiple Altium windows open without having more than one instance of Altium open. So like I'm looking at my completed schematic off to the side that y'all can't see. So that's pretty cool. Okay, so I think we have all of our major parts. I need, that was the USB-A, I think. Yeah, it was. Yeah, I need a handful of these. I need 5 of these because Max 30 or 48.99 has 4 I'm going to call them outputs. We all know they're duplex, so they're not really outputs, but you know what I mean. They have 4 outputs and 1 input, but the input is USB A. So but I also need power input. So and you can control C, control V in here. So 3, 4, 5. And then I know I need 2 switches. So there's that. And yeah, so let's get a little organized here. I'm going to move this, space bar turns at 90 degrees. So I can put that right there. Actually right there. And obviously in this case, I want to make sure all of my pluses line up. D++, USB 1+. Be a little awkward to wire them backwards. And then I want to put my switches not in the way. Whoopsie. I can put my regulator up here somewhere. I'm going to put my power in above that. And we can even start, there's a text string thing. If in Altium, tab key is your friend. So tab key will pause the program. You can see the little pause come up and it'll bring up a property window of whatever you're currently doing. So I'm going to make this text say VN, and I'm going to make it a lot bigger. So let's say bigger than that, 36. And then I just hit the pause button, it'll go back. And we use that in both the schematic side and the PCB side. And then I pasted it a bunch of times. I can double click and just change the text. So VREG, USB mux, and switches. Okay. So having things labeled in your schematic makes life easier later. So yeah, so please label things. And that's true of when you get to circuit board layout too, is there's no extra fee for extra silk screen. So please label the snot out of it. You can, like if you have I2C components where they have, or really anything with an address, it's always nice to print the address both in the schematic and on the circuit board, like stuff like that. You probably can overlabel, but for the sake of this discussion, you can't overlabel. Noting where ground points are and stuff like that. It's just always useful. So this is kind of, okay. So before I move on, I need to do a few things. So you'll notice we don't have any passive components yet, right? We don't have any resistors, capacitors, that kind of thing. So there's kind of a rule of thumb with devices like this, is that at every power pin, and by power I mean power coming into the device to power the device, we should put the typical value is 0.1 microfarad. That, based on what I've seen in industry, that just seems to be a standard. And couldn't tell you why. That might be a better Professor Willie question. But we always put one at the power input, or inputs if it has more than one. Every input gets a 0.1 microfarad resistor. And the reason being is just for voltage stabilization. We want it to have a nice, clean, stabilized voltage going in. We don't want to count on it however far it had to go from the regulator to get to the mux, which when we're, even though it to our eye is 1 millimeter, it's kind of far for nice stable voltage. Might get interference, that kind of thing. So we want to make sure we have a nice stable voltage at the input pin, at the voltage input pin. So we always put a 0.1 microfarad capacitor, and I'm saying that more than once to make sure you drill that in. So I've pre-made, Altium has in their miscellaneous devices their own capacitor. I pre-made a bunch of mine. You'll see it says 0603. And that's because I pre-made a bunch of generic non-polar capacitors that are of varying, you can see over here, 0402, 603, 0805, and 1206. There's a bunch of other sizes too. Actually, for those of you who are like extra interested in this, you should Google, or rather eBay, and look at some PCB rulers, like you're going to measure something ruler. And there's a bunch of ones that exist. And my personal favorite is the NVIDIA ruler. And what's cool about those is, first off, it's a circuit board, but they have a bunch of footprints on them. like circuit board footprints, and they're like always labeled. So you can in your hand see, oh, that's how big an 0402 is versus an 0805. And you can see what a QFN looks like, and you can, see all these things, how big trace widths are and stuff like that. So for those of you who are a little extra interested in this, you might consider looking at one of those. I know TI has a good one too. But anyway, so we're gonna call this guy a 0.1 U capital F. And we're going to select that exact part number later when we go to order parts or make a bill of materials or whatever. I could go to Mauser, find a part I like right now, and then put that model number into, or part number into manufacturer part search. And if they have it, I could just use that. That's perfectly valid. I personally choose to do it this way. Okay. Just because I would rather get the board done and then move on, and then make myself suffer through Mauser later. And so we need that. If you'll recall, the voltage regulator needed 2 capacitors. It needed on the input side, it needed a 1 microfarad, and on the output side, it needed 4.7 microfarad. I'm confident I can find both of those in an 0603. And I know I can because I already did. So I'm going to put 2 of those, and I'm going to call this guy 1 microfarad, and I'm going to call this guy 4.7 microfarad. And then what else do I need? I need does anyone know what a pull up or pull down resistor is? Anyone tell me that? So a pull up or pull down resistor is a way of kind of dictating to a device what state you want a pin at. So take these 2 things for example. This I put a little in before anything that's active low. So this device has a active low enable pin, which means I want to ground that pin. Okay. But standard practice is we would put, instead of connecting it directly to ground, we would put typically a 10K, but it doesn't have to be a 10K. I'm telling you industry standards here that I've seen. And we would connect that to ground. And we do that so that we can dictate the state of this pin. But there's a couple benefits to putting a resistor there. So like, let's say I hooked this up to a Raspberry Pi, okay? And I wanted to be able to turn this pin on and off. And so say I have a Raspberry Pi over here, Ras Pi pin 7, I don't know, whatever a GPIO pin is, not important. And I wanted to be able to control this pin. Can we see a problem if I don't have that resistor there? If I don't have that resistor there and I drive this pin high, I think we call that a dead short. I believe that's what that is. If I drive it low, we're fine. But if I drive it high, we might have a problem here. And so we typically will put a resistor there, which I just deleted. We'll typically put a resistor there so that we can actually, mess with it and do stuff to it. And the kind of current values we deal with at this for this kind of thing are very minimal, so we don't really factor that in. This is just intended to dictate the state of a pin. So I am now dictating this be at default ground, right? Because there's no current flowing to it, which means there's no voltage drop, which means it's connected to ground. So I'm dictating that this pin is at ground unless I tell it otherwise. And I'm not going to put a pin here. This is just going to stay at ground, but it's good practice to have a pull down resistor here. And a pull down just means it's going to ground. A pull up means it's being pulled high to VCC or whatever, which we're actually going to do with the switches. Any questions about that specifically? So what we're going to do with the switches, and you can take your time to make stuff pretty here. I'm trying to get through this quickly. What we're going to do with the switches is I do want to dictate their state. So I know that when I switch the switch, to position 1, I want pin 2 to be driven high. And when I switch it to position 3, then I want the pin 2 to be driven low. So again, we're going to utilize our pull resistors. So I'm going to put these guys here, and we haven't made our 3.3 volts yet, but that's what we're going to use here. 3V3, and where's ground? There it is, and ground. And I can connect all that up. And now at, whoops, don't do that. And now at this toggles back and forth. And so when I'm gonna call this C0, this is a port. You can call it a flag too, but I'm assigning pin 2 here to a port, which I will make a duplicate of here, and I will name that C0 also, and that's equivalent to me connecting them with a wire. Okay, so that keeps my schematic a little cleaner. And so these 2 yellow flags are connected because they're named the same net. So yeah, so now that switch is electrically hooked up such that when I move the switch to be connected to pin 1, it will drive C0 high, which means, remember these 2 are intended to make a binary, a 2-bit binary to select which output we're using. And so that'll drive that high. Okay. Then these guys get hooked up here. That's our USB-A input. Let's see. On this one, this is our power in. They have this little X. You should use this X on any pins you're not going to use. So since I know I'm only using this device for power, then I'm going to put little X's. That's just a good practice thing. That doesn't really do anything. That just tells the reader. Whoops, it has a. Okay, so this has a shell. That's the metal outer shell of the device, and just standard practice would be to connect the shell to ground. So we're going to do that, and then we'll connect the 5 volts up, and now we have our voltage input. Okay. And yeah. How we doing? Anybody got questions? Anything? This device has a thermal pad on the bottom. That's what EP is. So we're connecting that to ground, and obviously we're connecting ground to ground. All of these will obviously end up in these guys here. So we'll have to arrange those such that they all fit. But so yeah, that's where those will end up, connected there. And we'll hook up this switch the same way we hooked up the one above. We're going to give, there it is. We're going to give this guy his 3.3 volts. We're going to connect this guy to 3.3 volts because remember, this guy lives at, like when we go to lay out the board, this guy will be placed right next to this pin physically. Yeah. That'll get connected like that. And I think, I mean, maybe you can use your imagination. I think it's pretty straightforward what we're doing next. We're just going to finish connecting all this up. And that's pretty straightforward. The enable pin here, you could find this in the data sheet, but we just hook it directly to the 5-volt input. So it'll connect to the 5 volts, same as the input pin. The other side of your capacitors always get connected to ground. I mean, well, in this application. So that might, well, we're getting close to 8:30. I'm going to finish doing this, but that might well conclude what we're doing for tonight. How's everybody doing? I'd love some feedback. Is anyone totally lost? Is anyone following along pretty well? How are we doing?
I feel like I'm following along pretty well. I think one thing, I wish I made a predetermined library like with all this stuff in so that I could follow along with you in Altium, but I'm just watching you do it and it's helping like your button clicks, seeing how to actually like pull everything up quickly helps.
Yeah, I've made quite a few boards. That just comes with practice.
Right.
Yeah. But yeah, so like a pre-made library, especially of basic stuff like different size capacitors, resistors, that kind of stuff, is super useful. I made that, like probably after I had made one Altium board prior to doing Capstone, and I think I made it after that board, so I had it for Capstone, and good grief, was that awesome. And remember when I was showing y'all the cool thing, the tools, the IPC compliant footprint wizard, they have a not a chip array, a chip component. That's the standard resistor capacitor, non-polar capacitor. I want to be specific. So if you go on Mauser and you find you data sheets for various sizes, 06, 03, 08, 05, that kind of thing, and you go through this process, then you'll have, they follow the standard pretty well, like different manufacturers of parts. So I feel very comfortable that my 06, 03 footprint is good for basically anything. Maybe that's naive of me, but I've yet to have an issue. So yeah, I highly recommend that. And it's just good practice. Like it gets you practice making footprints and things like that. Cause I think I remember the first time I made a footprint, God, was I intimidated. Like even just going through this, the footprint wizard was intimidating. I mean, there's some complex stuff in here. Like that's kind of complex. There's all kinds of stuff, and it's easy to get intimidated by it. But most of this can be generated through the footprint wizard. So yeah, I would highly recommend that.
I'm also assuming you mentioned that you have YouTube videos that are very boring but go through everything. I assume like learning the footprint wizard and doing that would be on a YouTube video whenever you share those links.
I think so. It's been a while since I watched them because, as you mentioned, painfully boring. But yeah, I'm pretty sure I make a part in there, or at least start to make a part. Yeah. And there's a lot of stuff in there. That was a board I came up with on the top of just off the cuff. So the board itself doesn't make any sense. So don't put too much emphasis on that.
Okay.
It makes no sense. It has no purpose. I just threw some parts out.
Just for fun. Got it.
But yeah. So yeah, I will I'll try to have this recording uploaded, sometime either tonight or tomorrow morning, and I'll make it into a playlist, and then I will send that as well as that other playlist to Roseanne to send out to all of y'all. I guess one other thing I can show real quick. You see how we have all these red squigglies, like we misspelled something in Word? all that's complaining about is currently I have several C question marks, which, by the way, when you go to make a component, when you're in the schematic library, you'll see, well, that might be hard to see, but right there it says U question mark. That's what that you should put that. That's what you're supposed to put. Because then the software knows to look for that when we go to annotate. So you could go through here manually and say, I want this to be U1 and I want this to be U2. You could do that. They also have an annotator. Tools, annotation, annotate schematics. Pulls up a window on the wrong page. And then I don't really care what it names what. I just want it to name it. So update, accept it, and then validate. Everybody's happy. Execute. And now all of our components have names, and you'll notice the red squigglies went away. Red squigglies come up when there's a name conflict. So if you had two U2s, for instance, and yeah, anybody else got anything we want to talk about?
I actually have a question.
Sure.
So for on the switch, you know how you added the port? Was that just grabbed up from the toolbar?
Yep, that was this little yellow thing right here, and it pops up a little thing that says place port.
Okay, awesome. Thank you.
Sure.
How long are you, it might be in the emails, but how long are you planning on doing these videos? It's every week, the same date and time, right? Or every Tuesday at 7:30?
The next one will be on Thursday, unless we all have a conflict that day. At the same time, and I'm hoping to get done. But if we can't get done, then yes, we will go to next Tuesday at the same time.
Okay, so your plan is to go through everything in 2 sessions.
That's the goal. I don't know if I'll achieve it. So if not, then I'll do a third. Somebody asked, can you do an example of the 0.1 microfarad connected to the 3.3 volts again? Like, what is the idea behind putting that there? So I'm not going to pretend to be an expert on this. Most of what I know is industry standard related, not so much why is it done related. And that's just me being honest. But what I know is that this guy is here. Well, the value specifically is I couldn't tell you why it's 0.1 microfarad, which is the same as 100 nanofarad. You'll see that. But I have no idea. Just to be straight with you, I have no idea why it's that value. What I do know is it's here for voltage stabilization. So I'll go ahead and pull this over. This is the completed version of the board we're going to work on. Remember what I said about the number 3 key? There's a number 2 key. So where is it? C1. So you'll notice there's the power pin right there, or rather right here, sorry. And then our capacitor is nice and close to it. And we do that because our voltage came from over here, and we don't know what happened between here and here. It might have gotten some interference. It might have degraded a little. It might be a little bouncy, whatever. So that capacitor will help balance that voltage. It'll help stabilize it, rather. Hopefully that was helpful. And kind of the same thing with these capacitors up here. They're kind of serving the same function. These values were dictated by the data sheet, which is great because that means I don't have to think about them. I don't like thinking, neither do you. So the more that we can just say is industry standard or that the data sheet told us to, that's an acceptable answer in most cases. So yeah, these are performing basically the same function. They're just in this case stabilizing the input voltage, stabilizing the output voltage, and you're getting some level of battery-like behavior out of it, I guess. But I would say it's probably more for stabilization than anything. Anything else? There are probably no dumb questions. I say that jokingly. Please feel free to ask anything.
Just thank you for your time.
Yeah, so I guess that's my final question. And you're welcome. But is this helpful? Like, have we learned something? Is this, and this is an honest question. Has this already been helpful to those of you who are going to have to go design the board? Like, how do we feel?
It's been a lot more helpful than most YouTube videos. Yeah, I've enjoyed it so far.
Sweet. Thank you.
I'm not at the point yet where my team has to worry about making the board yet, because it'll be next semester, but it's pretty interesting just to see some things we'll have to do. But I'm really excited just to see like how this evolves into the next step.
Sure. And that's kind of why, for those of you, I'm assuming you're in 419, that's kind of what, for those of you who are, that's, I wanted to make a point to show that first bit where we go through this part. I mean, these are pretty lame requirements, to be honest with you. I wrote these right before we started, but obviously you'll have more thought out requirements than reasonably small, or I hope you will. And then we have, the conceptual block diagram. And then I think what's overlooked here is that, in my opinion, this is where you need to start thinking seriously about your circuit board. This is where you seriously need to be researching parts and understanding what's out there and what's possible. You need to be going, okay, here's something. Those of you who aren't familiar with a site called Adafruit need to become best friends with a site called Adafruit, because Adafruit has little modules. And I don't know, let's say I need a module for current monitoring. So if I want to monitor the current of something, I don't know if this is quite the right words to type. Okay, so here's an INA 219. I can now go buy this board, and SparkFun is another one. There's Adafruit, there's SparkFun, and then there's other ones too, but those are kind of the big two, at least in the US. And so I can go buy this board, and especially I can get ahead if I'm in 419. You can do this in 420, obviously, but especially if I'm in 419 and I'm starting to think about what parts I'm going to use and all that good stuff later on in the semester, I might ask my I don't know, what do y'all call them, advisor, whoever, if I can go spend some money and get some of these, and maybe, get this other board that does this, and start playing with them, hooking them up to an MSP 430 or something, and starting to kind of really think about, okay, what's possible? What can I do? Because I would say one of the number one advantages I have personally when I go to make a board like this is I have a pretty good idea of what's out there. A lot of you may not have that. And so what I would highly recommend, regardless of if you're the hardware guy or not, or gal, you'll go look on these websites and kind of poke around and start thinking, okay, we have this requirement. Maybe we'll need to use something like this. And that will help you later in choosing what parts. And what's great about picking a board like this is I can go down here, I can click on data sheet, and there's their schematic. So I can just copy the schematic. I can use the same parts that they used. This is a perfectly legitimate way to do prototyping. So get ahead on this. Start learning what's out there. And look at that. There's a 0.1 microfarad. I'm not crazy. So yeah, that for especially 422, obviously, but especially those of you in 419, start figuring out what's out there. Okay. If there are no other questions or anything, I think I will see you guys on Thursday, same time, 7:30 p.m., 1930. Unless like all of you have a conflict, and then we can talk about it. If many of you have a conflict, speak now or hold your peace. So yeah.
And that'll be on the same Zoom link, correct?
Same Zoom link. That is my, what do they call it? Personal Zoom link. So,
Okay.
so yeah, same Zoom link, same time.
All right. Thank you. See you Thursday.
All right. Thank y'all. Have a good one.
Thank you for your time.
Sure.
It was great. Thank you.